Thank you all for being here. What I want to present is opening electronic safe locks with ketchup and lasers. I have a few segments in this presentation. First, we will take a look at electronic safe locks and what interests me about them. Then we will talk a bit about laser fault injection and how that can be used to gain assets from your target. And I will say something about why these locks, why these circuit boards are covered in ketchup. But let me please introduce myself. I work as a security analyst and trainer at Riscure. My background is electrical engineering, study electronics. But currently I use advanced hardware attacks like side channel analysis, fault injection, to gain insight in the operation of the chip and to attack them. I'm also a key figure in the Locksport community. Currently, I'm the president of the Open Organization of Lockpickers. We are a group of people that are interested in locks and get together and discuss these things. We do a lot of things like organizing workshops, but also sharing knowledge on our blog, but also presentations like these. I think that's important. So let's take a look at electronic safe locks. These devices, they interest me because they have a small attack surface. In this case, it's only like an analog signal between the keypad and the device. Whereas other devices already use currently Bluetooth, mobile applications, talk to a server, whatever. That is currently what I'm not focusing on, just the simple locks that work standalone. It's already a good basis for the security because it's already like interesting. You have your keypad on the outside, there lives the battery, and there is an analog signal between the keypad and the internals of the lock. The lock, the electronics, makes a decision on do I open the safe door or not. But to attack the internals, you need to get through the safe door and vice versa. So it's already like interesting thing of hiding the important bits in a safe location. I have a few examples of electronic safe locks. They're just different grades, different types, and I just have 3 use cases. A lot of consumers currently get their electronic safe locks, and they are just simple devices. They're just easy to use. This should be reliable to some extent and also be fairly affordable. So in this case, it's just a 6-digit combination, the lock opens. Then for banking and pharmacy, they want different things. They want multiple users. They want logging on their devices. And sometimes they also implement time delays. These features also get a bit ported to the cheaper versions, but then they just get new features in return, like network connectivity or remote stuff. In this case, here I have a Paxos lock, which is quite a beefy lock. And you dial the combination with this rotary encoder, and it controls then 2 lock bodies, of which each lock body has already 2 locks in it. This is not just security, it's also a redundancy feature. Like if you're a big vault door, if one of these locks fails, then you can still open the device somehow. Then a lock that interests me quite a lot are these government special locks. In this case, this is from the US government. They have the FFL 2740 criteria, and this is the B version, is the latest version. And these locks have a lot of extra features, like you want them to be openable when a bomb has gone off, or you want to not be able to see that someone has used this lock from the outside with use of radio frequency. There are a lot of locks in this series, and the locks I'm looking at here specifically are from the KabaMas series. They have been doing this electronic lock design already for quite a long time. This is one of those locks. What we have, we have a dial on the front and a lock body on the back. This looks just like a normal mechanical lock, but in the head there is an LCD screen, but also a generator. So you have to spin the lock until it has is sufficiently powered, and then you can enter the combination and the lock opens or not. But it has a lot of lockout features in there. So if you dial too fast or not fast enough or rotate further than a hand should be able to rotate, then it will just say, no, you're not a human. I will not let you access this. We will take a look at this lock some more later. So how do I start with analyzing these locks? First, I got a lot of these locks from eBay and traded them with fellow lockpickers. This is a bit difficult, because it's they are quite heavy, and they are also not cheap devices. So you just buy them old stock and then try to see if you can match them together, see what works and what doesn't. But there are also plenty of locks that come like this, where there's just a hole in the circuit board. That's fine. I analyzed it and I used it, but it was just not functional as a lock. So where I started was to do some hardware reverse engineering to take the lock apart, take the circuit board apart, and then determine the function of each part, each subschematic. This is quite a nice thing, and if you can do this well, then you can do this a bit meditatively. But for me, sometimes it was just very frustrating. Where I started was just getting my hot air soldering iron and then just taking off the components of the lock one by one. This is just to show the complexity of a system, like even just the simplest of these devices are already a couple hundred components. But it's just great to be able to take a resistor, measure its value, and see if it's relevant for your circuit or not, or if it can be any other value. Then for the circuit board, once you took off all the components, you can just get a nice scan from it. And in this case, I put it into KiCad and then started tracing these lines. Like you place a component, in this case the pads are transparent, so it's a bit harder to see. You give all these pads a name, a net, and then you build your circuit from there. And then at the same time you build a schematic. It's quite a complicated system. Like here we have the LCD, the connector for the LCD, and the connections for the generator. And it has already like multiple power domains with its own bridge rectifiers and whatnot to have it function. This makes sense. Like you want to store energy to open your solenoid, but if you put your microprocessor on the same rail, then of course that can give issues. But I also think it's a lot more complicated than it needs to be. You can have, of course, your schematic, but the main ideas are, of course, hidden inside of the electronics. So there is a small EEPROM to store some non-volatile data, and you have your main microcontroller. So I wanted to figure out, like, can I get access to this AD51 microcontroller? And I did so with a few techniques. And I first started just looking at a universal programmer. The XKQ worked well for me. It's a Chinese model, and if you then change the firmware to an open source firmware, it worked quite well. But what I found was these devices are locked, fused, and encrypted. So that means just several of these security features of the chip are there to prevent me from accessing the memory. So then I cannot really attack the chip itself. So I started just buying a few chips from eBay. The problem there is it was not cheap, and most of these devices came pre-programmed. So here's an example. This is from Markus Heist. He made a widget called the MH interface. And yes, I got this code. I cannot put my own code in there because it's a one-time programmable. But it's not that big of a deal. Like, I would have wanted to program this chip myself, but I can still lock it, attack it, and see what sticks around. So one step was to go into the chip reverse engineering. This I didn't get very far, but it's still nice to show. Like, you can just decap a chip by just heating it up and using pliers to twist it open. Like, I didn't know. I learned from a YouTube video and later met the guy that invented the technique. And then I took some photos of the microchip. Here's the picture. In this case, of course, scaled down. But the detail is definitely there. Like, you can read the copyright statement of Intel on there quite nicely. And each of these are just individual connections in the chip. One goal of chip reverse engineering would be to selectively change memory. Like, for example, depending on the memory technology that they use, you can selectively deactivate portions of the memory. And another would be where you can read the content from the memory just by visually observing it. That can be done with some types of mask ROM. It was a nice idea, but I didn't get very far. And I might try something else, like looking at it with a scanning electron microscope or doing some microprobing. So a technique that I'm a lot more familiar with and that I use a lot at Riskier is called fault injection. It's generally perceived as a non-invasive hardware attack, where if you know how to do it, then it's quite a straightforward process. Just in quick terms, we have methods here, like voltage, electromagnetic, clock, or laser. We just choose one of these methods, and then we change the environmental variables of the chip. So if, for example, here I have a plot of voltage glitching, I vary the glitch voltage and vary the glitch length. And then each of my attempts will give me a point in this grid. And then each point is usually hundreds and sometimes thousands of attempts. In the green means the chip just operated like normal. Nothing was observed, nothing changed. And all the points in yellow means the chip crashed. We just couldn't communicate with it anymore. But on this boundary, interesting things start happening. And we give those the color red. Like the chip made a mistake. It executed +1 instead of -1, if that's what your program does. And we observe these changes. To do laser volt injection on it, we have to prepare the chip. And the problem here is already quite obvious. Like the chip is inside of a package, and you cannot go through it with your laser. And it's also very much a fragile device. Like there are different metal layers. We have the chip, and there are small bonding wires connecting the chip to the leads of the most common method is to use acid. So we etch from the top and get to the chip this way. This is quite a tedious process and definitely not something I am going to do at home. So my approach was just to go from the back. You need a slightly different laser setup, but it all works out. Because there isn't anything there preventing me to get to the chip. So I designed a small circuit board, mounted my chip upside down in there, and I started carving with a Dremel. Then you can just remove this cap and then clean it again with the Dremel. This worked remarkably well, and I did so later also for other chips and for other projects. Then we placed the device as a whole inside of a box, which has a microscope stage plus a laser. And we focus the laser on the chip, and then we do a grid search while varying the power, varying the timing, leads length, leads power, and it leads timing. And while we do so, we read the chip with the XKQ programmer, just seeing if we can change the operation of the chip somehow. So I did this in several stages. The basic stage is just to get an open sample where you know the content, and then you shoot at it with a laser to see if you can change the value somehow. And then for all these red dots, the value was changed in memory. This is just at this moment, like while I'm shooting the laser, the memory is changed, and so it is not a permanent effect. This is good to demonstrate that you can attack a chip, and then the next step is to lock the same chip and repeat the same attack again. And I reduce it to a couple points. This doesn't have to be the same points, but in this case they are. And then of one of these points, it gave me zeros instead of the memory value, and for the other one I got the memory values that I expected. But this was of course for the chip where I knew the content. I'm skipping a few steps here in the process just for the story. We repeated this attack on multiple locked samples and multiple real chips. And what I found was this location was the most interesting. And it sometimes gave me the correct values back, or at least different values. And sometimes it just gave me gibberish. So I used a bit of statistical analysis there to just get literally like millions of attempts, and then seeing which moment in time which bit was flipped, and then figure out what is the most probable content of the memory. Then there is still a small encryption layer on there, but it's just XOR tables, so nothing spectacular. And then what I got was the copyright statements from the code. I have here the X07, X08, and X09, but what we see is that this Dan L. Thompson, he did a very great job building the X07. He was not involved in the X08, and then he was again in the X09. And then the question, of course, is like, which of these products failed? And yes, it's the X08. Like, they tried to do it without him, and they couldn't manage it. To finish up the fault injection, I put in there that it could also be done on the cheap. Like, of course, these laser systems are not. So here's one setup that I tried earlier, which is using a Pico EMP. This is designed by Colin O'Flynn, which also is the person behind Chip Whisper and that product line. You can build it for 100 euros worth of parts. Just be careful with it. It's high voltage electronics. So yeah, just read up on this. Of course, fault injection is the only way. Like, this is always when you show someone your results, then they are like, I didn't even need to desolder this chip. So then I had another challenge, trying to figure out how this thing worked. He had a slightly different version of the microcontroller. I focused on one particular chip, but this 8051 was from an era where you could just get tens of these chips from the vendors, and they were just drop-in replacements for each other. That is definitely not the case anymore. And I tried to figure out, like, how does this work? Like, definitely Abrasive would have told me the solution, but I also liked to challenge myself and to figure it out. And it works on a quite old technique where you have your 8051 chip, in this case, in this socket, and I have my Raspberry Pi Pico in the rest of the picture. And what you can do is you can execute code from an external memory, and you can also expand the RAM inside of the chip with an external chip. In this case, the 8051 gets a clock signal from my Raspberry Pi Pico, and my Raspberry Pi Pico is both the RAM and the ROM. So it reads from it and it writes to it. And the secret sauce, and then also what I then rediscovered, is you can run your code from external memory, but you can apply it on internal memory. So in the code, I just said something like, read your internal data, then output it to RAM. And that works quite well. Later I found another solution by someone else where they have this 8051 and external ROM, and they just programmed it in such a way where you can get the content of the 8051 just output on the UART. So you can just hook up an FTDI and it will just print out the memory. This attack, of course, doesn't work on all chips. So just this particular version of the chip, the one that Abrasive found, it worked quite well. Now I have the content of the memory, the memory content, but I don't yet have a solution. Like, I've not yet found a bug or whatever. So that will be some future work. So this is the high tech side of the presentation, I now want to do some low-tech side. I definitely think this is interesting. Like it's just rediscovering an attack that already existed, and as it all begins, it's just someone puts out a video of this thing, and then yes, as an electrical engineer, I'm quite confused. The liquid shorts something, still opens the lock. The video is posted by Nigel Tolley. He is also a key figure. He has run Tool UK since, I don't know, 15 years or something. And this is the video in question, if you want to watch it later. But what happens is, this is a demo for their product. And they drill a small hole in the lock body. Then they fill the lock body with some kind of liquid, and then apply a voltage, and it opens the lock. They sell this kit for around 600 euros, and this might sound like a lot of money, but if you just look at turbo decoders, which are just lock geniuses, they make a lot of these tools, and they sell apparently quite well. And if you are a locksmith and you don't know how to apply this, and you buy the kit, I think if you fiddle with it in a weekend, then you can later apply it on real jobs. And then I don't know how many jobs it will take to pay back, but it's a complete kit, and you have all the tools. But I'm not a locksmith, and I just want to figure out like how these things work. So I had a few ideas, like these are just direct copies from the Discord, including spelling mistakes and whatnot. But the interesting thing is where Nigel mentions, like it just works and no one knows why. And that triggers me then to discover it. And I set some challenges about measuring it. Here's the lock that I picked up. It's just a fairly generic lock, but you have a few different regions. Like there's a region with the microcontroller, with the crystal, there's some power circuitry over there, and there are some big transistors to switch the current through the solenoid to open the lock. I just looked at it. I found that the microcontroller was an ST62, and it's quite an old device, but it's apparently a very popular device for electronic safe locks. Just opening more safe locks, I found this chip used more and more. So it is definitely something I want to take a look at sometime later. But I just did some quick characterization of the solenoid. And what I didn't know at that moment was that solenoids are not polarized. So that means if you supply it 9 volts or negative 9 volts, it just opens. And as far as transistors go, just in case you don't know, like transistors, we use them a lot as switches, but they are just amplifiers. Where a small current transistor has a high amplification, and a high current transistor usually has a low amplification. And that's just how transistors are built. But in the end, it doesn't matter if it's a transistor or a MOSFET or some other solution. It will all work very similar. This is the simplified schematic from the lock, where we have this is my I/O pin of the chip. We have a small transistor, a large transistor, and we want a current to pass through this inductor, which is my solenoid. In normal operation, it works something like this. We have the I/O, which just supplies a small current. This is mostly limited by R4, but there are other factors. And this is a small current into the base of transistor Q1. And this results in a large current from the collector to the emitter of the transistor Q1. This current has to come from somewhere. A small current flows through a resistor R1, and the most of the current comes from the base of Q2, and then the whole thing repeats again. This is just how the lock works. This is just the intended way. And then looking at the schematic, it might already be a bit obvious how to attack it. We just want a small current into Q1. So if we short these two positions, then the lock will open. This is definitely done as a technique, not just to connect these 2 points or just put a connect to the base of Q1. They call this spiking, where they just get wires into the lock connected in such a way where it opens the lock. It's quite a versatile technique. But what I wanted to know was, how does Liquid attack this lock? So I put it into LT Spice. Spice is a simulation package for electronics, and LT is Linear Technologies. They still supply this package, even though it's already like 20 something years old. On every node, I placed a name, and then I connected all the nodes together with resistors, just to simulate the liquid. Then I varied the resistor, and then figured out that anywhere between 5,000 ohms and 20,000 ohms would put enough current through the solenoid to open the lock. Then I wanted to figure out like what type of liquid works best. Like we already were told ketchup would be a good guess, others were already using mustard or something else. So I just wanted to figure these things out. I used a total dissolved solids meter and an electrical conductivity meter, where they say, like very scientific-y, Siemens is expressed as 1 over the resistance. And then I tested a lot of liquids, and my kitchen looked like this. And yeah, I don't have the real measurements anymore, but what I got was these are close enough. I find this quite interesting to do these relatively simple experiments, and then I'm like, oh, I expected this liquid to be an insulator, and then it wasn't. Then it was a very good conductor. It's just fun to see how these things work. But let's just put this into practice. I will open OBS and then share what I have on my table. Can we see it? Yes. Okay. So here I have my electronic lock. This is a Lagarde. This is just a normal consumer lock. So if I press a combination that doesn't work, then it will just not open the lock. And if I press the right combination, 1, 2, 3, 4, 5, 6, then the bolt can be retracted. In this case, the keypad and lock should be mounted like this, where you dial the keypad. It's a wrong keypad for it, but that should be normal. And then you can reset it either by turning the dial again, or in this case I just put a piece of tape on there. So it's locked again. I now remove the keypad. I don't need it. And I have one more wire connected, which is my power supply. In this case I just turn it on. It's 9 volts, 0 amps currently outputting, and it doesn't open the lock. I turn off the power supply again, so it doesn't, because I need to be quite quick with it. So now we open the lock and we see the circuit board. It's slightly more complicated than the previous one, but it all works the same. And I have my ketchup. This is, well, not in focus. Apparently, without added sugars and salts, it works fine. I put some ketchup on the lock. Let's see if this works right away. Yes. Okay, that's great. Yes. So now there is ketchup on my lock, but what I do is I just clean my circuit board with some alcohol. Sometimes I put it into yeah, dishwasher might work. I was thinking of an ultrasonic bath. I didn't bring it, but it will be fine. The ketchup is of course a bit corrosive, so I wanted to get off the circuit board as soon as possible. And it was great that this demo worked. So to wrap up, yeah, there are always more locks to attack. There are always more exploits to rediscover. I have to mention then that my projects always seem to be exponential, and or at least that's what people say. but it's true. Like once you have one lock, does it also work on all the other locks? If you just want to try it. And after all this, you think electronic locks are interesting, and maybe you even have ambition. Then I can definitely recommend just playing around with these locks. So where would you start? I would recommend to get a lock like this. I have one here. It's called an Ambition. In this case, it's just a normal electronic safe lock with a keypad and a lock body for inside of the lock. But it also has a key override. And I don't think I need to really explain this, but if you have your circuit board and there's a nice big hole in there for your key, then maybe you also can reach in there and get to the motor contacts. This is work from Devo over at Lockpickers United. And there are several other people looking at this specific lock. The reason for it, I believe, is because people already found issues with it, and then they are just like, okay, if there are already issues with it, then I can rediscover them. And then people can help me with this. It's quite nice seeing all these people progressing with this lock and then asking questions on how do you draw schematics like this in KiCad, and then it can help them and explain there as well. Other work that is just good to mention, Plor did a very nice presentation for DEF CON quite a while ago, which is side channel analysis. So he uses the current consumption of the device to figure out a combination, and also did timing attacks on this. Michiel Hubler, he took apart the X09 way before I knew about them, and analyzed them mechanically, not the electronics, but mechanically. Mike Davis is a fairly recent presentation, which also goes into power side channel analysis, but he attacks most of these logs from the Kaba MAS series. And then the last one I wanted to mention is Lance. He wrote the book Electronic Safe Locks and How to Defeat Them. In this case, it's a spiking attack. Getting into the lock, connecting parts of the circuit board together, opening the lock. But what is great about his work is where he just gets, not just obsessed, but he has like 200 different locks open and shows you how they work and how they don't work and those type of things. And then talking of books, this book now exists, which is written by Jos Weijers, Walter Belgers, and a few friends from overseas, Matt Burrow and BNE A2C from the United States, and also Nigel Tolley from the UK. They haven't asked me anything about this book in the pub in 15 minutes. Okay, that was all. Are there questions?
So you just put a dab in a pretty specific spot. Does it also work if you cover the whole thing? Because like the attack from the outside would be drilling a hole and putting the ketchup in. Have you tried that?
So the question is, currently I just put a very careful dab of ketchup on my circuit because I know this circuit and I know that's the place where it needs to be. Does it also work if you cover the whole circuit? As that would be, of course, the intended solution if you drill from the outside. Yes, it works, just a lot less reliable for this particular lock. And then reliability is, of course, like, do you want to demo that?
Why do they not coat the board?
So the question is, why do they have coating on there? Yeah.
The board you attack doesn't have conformal coating. Why
Yes, it doesn't have conformal coating, that's correct. In this case, it's already a board that has been there for at least 10 years, maybe even 20 years. And they wisened up, so of course the newer boards have conformal coating. They also have other countermeasures against it. Are there more questions? Okay, thank you all for listening.